Hey everyone, welcome back. In this video, we are going to do a quick review of continuity, and then we are going to review questions from units 1.10 to 1.13 for the AP Calculus exam. So first things first, it's important to know the three requirements for a function to be continuous at a point. So they are over here on the left here, numbered 1 through 3. So first of all, f of a must be defined. What does that mean? It means there must be an output value. So for example, if we had something like that, and this was just left as an open hole, f of a would not be defined. So what we need is we need it to be filled in, right? We need it to be defined. Second, the overall limit must exist. In order for the overall limit to exist, the limit from the right must equal the limit from the left. So limit from the right must equal limit from the left. Lastly, all three of those things must equal each other. So limit from the right must equal limit from the left must equal the output value. So those are the three requirements for continuities. Now let's talk about the three types of discontinuities. First is a removable discontinuity. So that is where, kind of like the picture I drew earlier, that's where you have an actual hole in the graph. This is not continuous, right? Another easy way to think of a continuous function is just, can you draw your pencil or pen through it without having to pick it up? Right here, that would not be the case because I would have to jump over that little hole. When does this happen? This happens with rational functions. So those basically are fractional functions. So if I had something like x plus 1 times x minus 3 over x plus 1, this here, because those can cancel out, that would create a hole in the graph. So that's when you want to be on the lookout for removable discontinuities. Second, jump discontinuities. That's where your function literally jumps, right? Something like that, and then it goes to something like that. This happens oftentimes when you have piecewise functions. So that's where you want to look for jump discontinuities, is if you're given a piecewise function. Lastly, infinite discontinuities. These have to do with asymptotes, right? So again, these happen with rational functions. If you have something like 1 over x plus 3, right, you're going to have a vertical asymptote at -3, right? So something like this, you definitely want to be on the lookout for infinite discontinuities or vertical and or horizontal asymptotes. Okay, now let's jump into some practice problems. Okay, so the first question comes from Unit 1.10, which has to do with the different types of discontinuities. So this gives us f of x, and it says the function f is defined above. Which of the following statements is true? So first thing I'm noting is that the function basically has this same function rule for all values except for 2. So, and then when I'm looking at this, first thing I'm looking at is I'm noticing that this is a rational function. So I'm going to be on the lookout for infinite discontinuities in theory, and then also holes or removable discontinuities. So first things first, I'm going to have to factor this out to see if I actually do have a discontinuity. So factoring the numerator, I'm going to set it up like so. I'm going to factor this using what I like to call the traditional method of factoring, which is basically just where I figure out what really just like what multiplies to that and adds to -3, keeping in mind that I'm going to have the 2 here. So another little hint I'm using here is I'm using the fact that with these types of problems, these are almost always going to cancel out. So I'm kind of keeping that in mind, and I'm already assuming that I'm going to have this term in my numerator. But anyways, to finish this off, in order for it to multiply to -2, this is going to have to be a +1. And then just to verify that it multiplies out to -3, or I'm sorry, I meant to say adds to -3, here I would have a -4x, here I have a +1x, which in fact gives me that -3x. Okay, so as I was saying, these are going to cancel out, and now I'm left with 2x plus 1. So what does that mean? That means if I were to graph this like this, I would actually have a simple linear function like y equals 2x plus 1. So I would have a y-intercept of 1 and a slope of 2. So maybe something like this. Excuse my poor drawing here. So this would be y equals 2x plus 1. But then at x equals 2, I would actually have a hole in my graph. So at, let's see, 1, 2. There we go. So wherever this is, I would have an open hole here. So my goal is to see if that would, in theory, output 7, as that's going to tell me whether I have a removable discontinuity here or not. So in order to do that, all I'm going to do is I'm going to take what I'm left with, this 2x plus 1, and I'm going to plug 2 in for x. So then I would get 2 times 2, which is 4, plus 1, which is 5. So this open hole would be at 5, but I know because of this, I know my function is actually going to output 7. So then basically at 7 up here, I would draw this closed end dot. So now going back to the actual question, which of the following statements is true? Well, now I've shown that I, in fact, have a removable discontinuity at x equals 2. So this would be answer choice B. All right, moving on. Okay, so this question states the function f has a jump discontinuity at x equals 3. Which of the following could be the graph of f? So this question requires us to know the different types of discontinuities and what they look like. So I know a jump discontinuity is where my graph basically jumps from one value to the next. So number A, or I'm sorry, letter A here, this has what we would call a removable discontinuity, this open hole or that circle, so it would not be this. B doesn't look like it has a discontinuity at all, so that would not be correct. C, this is exactly what I'm looking for here, right? How these output values actually jump from one value to the next, so this is correct. And then just to go through D, this has an infinite discontinuity, right? That has a vertical asymptote, so D would also not be correct. All right, moving on. Okay, this question states the graph of a function f is shown in the figure above. At what value of x does f have a removable discontinuity? So again, we have to know our types of discontinuities. We've already talked about this one a couple of times now. So removable discontinuity is where you have an open hole in your graph. So just going through these quickly, at 1, we do in fact have a discontinuity, but this is a jump discontinuity. So this would not be correct. We can eliminate that. At 3, this looks great, right? We have this open circle with its output value here. So this would be our correct answer. Let's just go through the others just to go through them. So at 4, we do not have a discontinuity there. So this is fine. And then at 5, we have an infinite discontinuity, right? We have this vertical asymptote here. So it would not be that. So the correct answer would be B. Okay, so this question has to do with topic 1.11, which is continuity at a point, and it says let f be the function defined above. Which of the following statements is true? So just doing a quick vertical scan of my answer choices, I am basically noticing that I am looking for whether the function is continuous or not and why. So in order to be successful on this problem, I have to remember my 3 conditions for continuity at a point. First, f of a must be defined. 2, it must equal the overall limit, which means it must equal the limit from the right, must equal the limit from the left. Please ignore my sloppy and quick notation and bear with me there. So now let's check these one by one. So first of all, does f of a exist? Well, in fact, it does not exist. How do I know? Well, looking up here, this is only defined for x is less than 1, and this is only defined for x is greater than 1. We do not have it, neither of those have an equal, right? Neither of those are less than or equal or greater than or equal to. So actually, in this case, the function is not continuous because f of 1 does not exist. However, just for the sake of the lesson, let's go ahead and find these one-sided limits just so you can see how you would solve this if this was not the case. So this is going to be from the left and this is going to be from the right. So the limit from, actually, let's do the right first just because of how I wrote this out here. So from the right, if I went ahead and plugged in 1, I would get 1/2 times 1 squared minus 1. I'm going to actually write this as 2 over 2, anticipating that I'm going to need a common denominator, and then plus 5 over 2. So simplifying this, this is just going to be 1/2. 1/2 minus 2 over 2 gives me negative 1 over 2, plus 5 over 2 gives me 4 over 2, which simplifies down to just 2. Now let's do the limit from the left. This one's a little more simple. 2 to the first power is simply 2. So this tells us that the overall limit does in fact exist and is equal to 2. However, bringing it back around, this function is still not continuous because f of 1 does not exist. All right, moving on. Okay, this question is from 1.12, which has to do with continuity over an interval. So it states the graph of the function f is shown above, which in this case is to the right. On which of the following intervals is f continuous? Okay, so just again, quickly scanning through my answer choices, I'm going to kind of just draw these little imaginary vertical lines here. Know that those are not asymptotes. That is just what I am drawing to break up my intervals for myself. I can actually draw them as solid lines. Maybe that's better so they don't look like asymptotes. Okay, 2 is here, and then 3 is there, and 5 is just about there. Okay, good. So I'm looking for intervals with basically where the function is continuous. So from -1 to 1, this is my first interval. This is not continuous. Why? Because I have an infinite discontinuity right here, right? You can see that dotted line there. So this is no. From 1 to 2, again, this is no. Why? I have a removable discontinuity there, so this would not be continuous. Now from 2 to 3 here, nope. Again, I have a discontinuity. I have a jump discontinuity, so not there. And finally, 3 to 5, this all looks good, right? I can draw my pen along this function like so without lifting it up, which is just kind of a quick little shortcut to use to test for continuity. So the correct answer choice here would be answer choice D. Okay, so this is a 1.13 question. This has to do with removing discontinuities. So it says, let G be the function defined above, where K is a constant. For what values of K is G continuous at X equals -3? So what I have to do here, remember, in order for a function to be continuous, the output value has to equal the limit. So basically what's going on is this is my function rule for everywhere except for X equals -3. And then it's going to equal K when X is 3. So I have to make sure that I'm basically filling in that hole with where this function would otherwise output it if this was not the case. So I know that sounds a little confusing, but I'll try to draw you a picture as I go, and hopefully that will make more sense. So first thing I have to do is factor it. So my numerator is a difference of squares. That factors down into x minus 3, x plus 3. And then in my denominator, I'm going to take out my greatest common factor of 4, and I'm left with x plus 3. So these are going to cancel out, which again is going to create a hole in my graph. So basically what I would have here is 1/4 times x minus 3. I'll show you why I'm doing this. I'm just going to distribute the 1/4 in. I'm going to get 1/4 x minus 3/4. So basically, this is just the equation of a straight line, right? That's going to have a hole at x equals -3. So if I were to draw this quickly, ignore this graph because it is not going to be drawn to scale, but I'm going to do my best. Let's just say -3/4 is here. And I have a slope of 1/4. So I don't know, let's just say something like this. Again, ignore this because this is obviously not drawn to scale. And then wherever -3 is, I don't know, let's say it's somewhere out here, I would have an open hole here. So basically what I have to do is I have to give my K value, or I have to make K so that my output value basically fills in that hole. So I have to figure out where that hole would be. So in order to do that, I'm going to take this X value here, which is -3, and I'm going to plug it in to my equation here, which is this, and just see what I would get. So my output value, or my Y value, would be 1/4 times -3 minus 3, just like that. So again, all I did was I plugged in the X value of my hole into this function for X. So now let's go ahead and just simplify that. I'm going to get 1/4 of -6, which is the same as -6/4, or simplifying, I would get -3/2, which is answer choice B. So again, just to kind of bring it back around, what I've done is I've said, okay, well, I've said when x equals -3, I've basically forced this function to output -3/2, which is what my function would have otherwise output if it did not have that hole in the graph. All right, thanks so much for watching, and I'll see you in the next one.